Hello everyone, hope you are doing well. Welcome to the online platform Civil Technobricks. Guys, here we will tune for the instantaneous decoding of the conceptual knowledge in the field of civil engineering, where study elaborates decoding the earth to build a better world. Today we will go through the core concepts of structural geological components like outcrop, deep, and strike in the view of civil engineering domain. So in today's lecture, we will discuss the structural geological components with reference to the spatial characteristics on the civil engineering applications. Here, the most important concept in structural geology are the outcrop, deep, and strike. These parameters helps engineer to understand the orientation and behavior of rock masses beneath the ground surface. With reference to that structure, or we can say that the orientation, the civil engineer must have to decide their policy of the foundation before constructing any type of dam, tunnel, highway, or foundations for big massive structures. Engineers must know how rock layers are inclined and how geological discontinuities are oriented. Deep indicates that the steepest slope of a rock layer, while strike represents the horizontal direction of the layer. Means deep indicates that the steepest slope of rock layer. Here the deep is nothing but a steepest slope, while strike is the horizontal direction of that layer which is steep. So understanding these structural components is extremely important because geological conditions directly influence excavation stability, seepage, slope failure, and structural safety. The tip of the iceberg, that is outcrop. With reference to the image displayed, the surface landscape and the subsurface bedrock which are beneath to that landscape. So outcrops are on the topmost surface of the earth. At the same time, below to that, there is a subsurface bedrock with reference to its texture, orientation, and characteristics regarding slope, regarding shape, likewise. The slide explains that the concepts of outcrops. An outcrop is the visible exposure of bedrock on the earth's surface. In the most of regions, the rock formations are hidden below soil cover, vegetative material, and water bodies. So therefore, outcrops become valuable sources of geological informations. Civil engineers and engineering geologists study these exposed rocks to understand the orientation, strength, weathering condition, and structural features of that rock masses which are on the surface of the earth, just like outcrops shown in the image 1. Outcrop observation helps in predicting underground geological conditions for construction projects. With reference to this information, it is important to plan the construction of dam, highway, bridges, tunnels, and foundation system with the help of outcrops. The scattered outcrops and the structural modeling. How we can decide the model based on the structural condition of the rocks with reference to the outcrops. So we study how engineers develop structural geological models using scattered outcrop data, where the outcrops are not continuously exposed everywhere. Engineers collect that geological observations from limited locations and interpret the hidden geology between them, or relationship in between them with reference to its types, characteristics, texture, or any index property. Topographical maps, satellite images, and aerial photographs are more helpful to identify that geological boundaries and structural trends which are on the earth surface with reference to the contours, with reference to the elevations, or with reference to the deep or depressions. Using these observations, engineers prepare structural models showing bedding orientation, rock layers, fault characteristics, and subsurface rock continuity. These models are extremely useful in planning excavation works, tunnel alignments, dam foundations, and slope stabilization measures. The deep, the intensity of the slope. So deep is the angle between the bedding plane and a horizontal plane. Deep is the angle between the bedding plane with reference to the horizontal plane. So horizontal plane is shown where protractor is there and bedding plane is there. So with reference to that bedding plane, we have to measure the angle with reference to the horizontal plane. So it represents the maximum slope of the layer and is always measured in a vertical plane perpendicular to the strike. The slides explains that the concept of dip, which represents the steepest, or we can say that the steep inclination of the rock layer, and is always measured in a vertical plane perpendicular to the strike. Dip is an extremely important parameter in civil engineering because it controls the stability of rock slopes and underground excavation activities. When bedding planes dip toward an excavation phase, the possibility of sliding or wedge failure increases significantly, just like shown in the image. Therefore, deep measurements are essential during geological investigations of rocks, dams, tunnels, or any type of foundations. The strike, where the direction of continuity, we can say that strike is the bearing, or we can say that the direction of a horizontal line on the surface of an inclined bed. So where inclined bed or inclined surface is available on the earth surface, then we can check that strike of that surface. Strike is always at right angles to the direction of true dip. So where is the true dip? Which is downward from that surface. So we can take the perpendicular to that deep line and we can measure the strike angle with reference to them. The strike, which represents the horizontal direction of a rock layer, strike is defined as bearing of a horizontal line on an inclined geological surface. Which is an important point is that the strike always lies at 90 degrees to the direction of true dip. Most important point for competitive exam also, that strike always lies 90 degrees to the direction of true dip. In civil engineering projects, strike orientation is used to determine the safest direction for excavation and tunnel alignment. By analyzing strike patterns, engineers can identify structural trends and predict the continuity of geological formations across the project area or the site selection for the project. Most important concept, true dip versus apparent dip. What is meant by true dip? The maximum inclination measured perpendicular to the strike. And what is meant by apparent dip? The inclination seen in any vertical section not perpendicular to the strike. It is always less than the true dip. Most important concept for the competitive exam point of view also. So here the comparison of true dip versus apparent dip is shown. True dip is the maximum inclination of a geological layer measured perpendicular to strike. When measurements are taken in other direction, the observed inclination becomes apparent dip. So at the same time, when we are checking the true dip, at the same time we can check the apparent dip also. Apparent dip is always less than the true dip value, always. So for civil engineering point of view or applications of civil engineering point of view, such that slope stability analysis, tunnel excavation, dam foundation design, accurate identification of true dip is extremely important to avoid unsafe designs and incorrect geological interpretations. The tools of measurement. So which tools we can use to measure? Two tools are required, compass and clinometer. Compass, which measures the bearing, or we can say that the strike relative to the magnetic north, that is true north or the north direction. Clinometer, which measures the vertical angle just like the dip with relative to the gravity, so modern digital surveying tools and GPS segments have further improved the precision and reliability of structural geological investigations, where the field measurements collected using these instruments, which helps engineers to understand the orientation and deformation of rock masses. The clinometer measures the deep angle of rock layers with reference to the gravity, whereas A geological compass measures the strike direction relative to the magnetic north. Geologist shorthand means the three concepts are there. First is the inclined strata, second will be the horizontal strata, and third will be the vertical strata. See the images. Inclined strata, the orientation of rock layers. With reference to that, the geological symbols used in structural mapping, or we can say that structural study or analysis point of view. The strike and the dip symbol acts as a shorthand representation of rock orientation on the geological maps. So here we are dealing with the representation of rocks. So strike and dip symbol acts as a shorthand. Long line, or just we can say that long line represents strike direction, while the short tick marks indicate dip direction. So dip directions are by the short tick marks, while long line represents the strike direction. The number of written beside the symbol, the number written beside the symbol represents the deep angle. Means here 30 is a deep angle, and that line nearby to the 30 which shows the deep. These symbols allows engineers and geologists to quickly interpret geological structures and understand subsurface conditions, beneath the surface conditions during engineering investigations, which are most useful for site selection criteria for any massive construction activities. So here long bar is equal to strike direction and short tick is equal to dip direction, where number is equal to dip angle. Moving towards the communication point of view, the communicating the complex structures. So here three major components are identified, which are specialized symbols indicate deformation and displacement, or we can say that change in their original space with reference to the coordinates, such as overturned beds, plunging folds, and fault movements in Georgia, just like case study. So specialized geological symbols are used to represent faults, overturned beds, fault movements. Likewise, overturned beds indicate that rock layers have undergone severe deformation or displacement due to tectonic forces or vibrations. Fold symbol show the plunge direction and orientation of fold axis, while fault symbol indicates the displacement direction. These structural interpretations are extremely important in civil engineering because faults and folds significantly influence the stability of dam, tunnels, foundations for each and every construction projects. That with reference to the alignment of dam, what are the engineering risk, or what is the level of risk with reference to the dam alignment? So specialized symbols indicate deformation and displacement, such as overturned beds, plunging folds, and fault movements in Georgia. With reference to that, stability and critical risk. So owing towards stability point of view, we are seeing the dam wall where water is stored on the upstream side. With reference to that, rock textures and orientations below to that dam wall, deep upstream, water pressure closes joints, rock layers resist sliding. These are the most important stable foundations. But what will be the critical risk foundation? Here the water is stored in the upstream side, but that whole water will percolated to the downstream side, and we will may get overturn effect. So down, deep downstream, potential for catastrophic sliding failure. Water lubricates bedding planes, just like the leakages, or we can say that seepage losses. When bedrock dips upstream, reservoir water pressure tends to close joints and improve stability, just like image 1, where when bedding planes dip downstream, water pressure may promote sliding along the discontinuities, just like image 2. This condition can create catastrophic instability and increase the possibility of structural failure. Therefore, detailed geological investigations are mandatory before site selection criteria for any dam site or any designing of the reservoir structures. About the stability, With reference to the tunnel excavation, just we are excavating the whole rocky masses for the tunnel. That tunnel may be for the transportation point of view, or any water transport point of view. Here two considerations: driving with strike and driving against deep. Okay, so with reference to the texture available of nearby rock masses, we can select the actual location of the tunnel. Bedding parallel to roof, overbreak, roof fall risk, and bedimentary bedding planes. Bedimentary bedding planes are parallel in image 1. At the same time, in image 2, we can see that the bedding perpendicular to bore, that are the orientation of the rock masses. Here natural anchoring effect is there. Also self-supporting capacity of the bed rocks is also mentioned. So driving against deep and driving with strike, which shows that the stability in tunnel excavation. Proper structural interpretation is most important for the civil engineering point of view, which minimizes excavation hazards and improve the underground stability. Tunnel orientation must be selected carefully based on geological structure, whereas the excavation act against deep often creates a natural anchoring effect, we can say that, which improves the self-supporting capacity or stability. When tunnel excavation is performed parallel to the strike direction, bedding planes may become exposed along the roof, increasing the risk of roof fall and overbreak. Stability point of view, we have to also check the slope, stability, and the daylight envelope. So here the concept of slope stability and the daylight envelope occurs when bedding planes emerge at the slope face, creating a potential of sliding surface. Creating the potential of sliding surface. So here the image shows that where the highway is constructed at the valley portion, nearby to the valley portion, with reference to the orientation of rocky masses beneath to that highway embankment. The bedding deep angle is there. With reference to that bedding deep angle, we have to mark the slope cut angle with reference to the daylight envelope, and which give the friction angle with between the bedding deep angle. So planar failure, rocky masses may get disturbed from top surface of the hill, and which gets slide down towards the road surface, but it can't damage to that roadway. It just slides and stop at the bottom. If the bedding deep angle becomes greater, if the bedding deep angle becomes greater than the friction angle but smaller than the slope angle, planar failure may occur. Planar failure may occur. Under gravity forces, the rock block slides towards the excavation phase. Therefore, engineers must analyze geological orientation carefully while designing highway cuts, open excavations, and hill slopes. Here we are interpreting the data. So interpreting the data with reference to the field observations. By observing the reversal of deep direction along a traverse, we can identify major subsurface structures like this anticline, or we can say that the syncline nature of the rocky masses below to the earth surface. The surface strip map is there, and the subsurface cross section is there at the below to that surface strip. By observing changes and reversals in the deep direction along a traverse, engineers can identify folded structures such as anticlines or synclines. So surface observations are used to prepare subsurface geological cross sections. These cross sections most helpful for visualizing the underground structures and understanding the rock continuity. Accurate geological interpretation is most essential for safe design and construction of foundations for the tunnels, dams, slopes, and other major civil engineering construction activities. Stay tuned, guys. Happy learning.